In this video lecture, we'll be solving this problem, count complete tree nodes. So in this problem, we are given the root of a complete binary tree and we have to return the number of nodes in the tree. So what is a complete binary tree? In a complete binary tree, every level except possibly the last level is completely filled. That means for any level, let's say h, there are 2 raised to the power h nodes at that level except the last level. This is true for every binary tree because each node can have at max 2 children and all nodes in the level are as far left as possible. So this is the case with the last level where the number of nodes can lie between 1 and 2 raised to the power h, where h is the last level, and the nodes which are present at the last level are as far left as possible, and we have to count all the nodes of this tree. Fine. So and we have to design, and the optimal algorithm that we will arrive at must run less than the linear time complexity. So this is a requirement of the problem. In the input will be given the root of the binary tree, and in the output we have to return an integer representing the number of nodes in the given binary tree. In the constraints, the number of nodes in the tree lies in the range from 0 to 5 into 10 raised to the power 4 or 50,000. That means the maximum number of nodes that can be present in a particular tree can go up to 50,000, while the largest value a node can have also goes up to 50,000, and the tree is guaranteed to be complete. So let's better understand this problem statement using an example. So here we have an example. This is a complete binary tree. How do we check for a complete binary tree? So this is level 0, and at level 0 we must have 2 raised to the power 0 nodes, and this is the case. 2 raised to the power 0 is 1, and hence we have 1 node at this level. Then at level 1 we must have 2 raised to the power 1 nodes, that is 2 nodes, and indeed we have 2 nodes at this level. Then we arrive at the last level where we must have nodes between 1 to 2 raised to the power 2, that is 1 to 4, and we have 3 nodes at in this level. And the another requirement is that all the nodes must be as far as possible, and this is the case here. All the nodes are placed as far as possible because for node number 3 we have only one child, that is 6, and this child is placed at the left side of this node, or it is the left child of this node 3, and hence all the requirements of the binary tree, a complete binary tree, are satisfied. Therefore this is a complete binary tree. So we'll pass this root of this binary tree into our function which evaluates the number of nodes in the given binary tree, and that function must return me the number of nodes in this tree, and the answer for this particular tree would be 6 because we have 6 nodes in this tree, that is 1 2 3 4 5 6. Fine. Let's see how we can solve this problem. The intuition or approach to solve this problem is simple. The most naive approach to solve this problem is simply traverse the given binary tree. That is, start from the given root node, traverse this binary tree, and just traverse this binary tree and visit all the nodes of this tree. While visiting, we simply keep a counter which counts the number of nodes that has been visited while traversing the given tree, and finally we return that counter from our function. So this is the most naive approach, and we know that for a tree traversal there are 2 algorithms. So one of the algorithm is depth first search, which is a recursive algorithm to traverse a given tree or graph, and another approach to solve this problem is breadth first search or BFS, which is an iterative algorithm to traverse the given tree or graph. These are the 2 basic graph traversal or tree traversal algorithms which can be used to count the number of nodes in the given binary tree. So let's discuss these algorithms one by one. So let's discuss the depth first search approach to solve this problem. In the depth first search approach, we simply use the function D. So we simply use this function DFS, which takes in the given node. We simply use this function DFS, which takes in the given node, and it traverses all the nodes of the given tree starting from this past node. And this is the visited array that we used to visit or to mark the nodes which has been visited while traversing the nodes in this function. So how does this algorithm work? We simply call this DFS function at the root node, that is node 1, DFS1, and then we mark this one as visited. That means the node 1 has been visited. So this has been visited. So we mark it as true. Then we check for the left child of this tree, and we see that there is a left child for node number 1, that is this one. And hence this DFS function will recursively call itself for the left child, that is DFS2. Then we simply mark 2 as visited. Similarly, this function, we have left child for node number 2, and hence this DFS function will recursively call itself for node number 4. While traversing like this, we simply keep a global variable, let's call it count, which was initialized to 0 initially, and while visiting each node, we simply increment this variable by 1. So at this function call, we have count as 1. Then at this function call, we have count as 2. While at this function call, we have count as 3. And at this function call, we visit this node 4 and we mark it as visited. Then these 3 nodes are visited, and this node 4 do not have any children. Therefore, we backtrack to the parent node, that is node number 2 here. Then we check for the right child, that is node 5, and we recursively, and this DFS function will recursively call itself for the right child, that is DFS 5, and we mark this node as visited while the count is incremented to 4 here. Then we see that 5 do not have any children, and therefore we backtrack to the parent node. From node 2, we have explored its subtree, therefore we backtrack to the calling function at the parent node, and hence we backtrack to DFS1. So here we have visited the left subtree of this node 1. Now we visit the right subtree of this node, and in the right subtree we call this function DFS. So this function will recursively call itself for the right child, that is 3, and here this is visited, node 3 is visited, and the count becomes 5 here. Then we visit the node, then we have visited node number 3, and for this node we visit the left child of this node, that is 6. So this will recursively call itself for the left child, that is DFS 6, and we mark it as visited while the count is incremented to 6. Since 6 do not have any children, we backtrack to the previous node here, and 3 do not have any right child, then we backtrack to the parent node, which called the function at this node. Now we are standing at the root node, and our answer has been updated to 6. Fine. That means the number of nodes in this particular tree are 6, and that is the answer. And we can see from the visited array that we have visited all the nodes in the tree. Fine. So that's how the depth first search algorithm will work here. So let's see the implementation for this algorithm. So this is the implementation for the depth first search algorithm that we discussed in the previous slide. It takes in the root of the tree, and if the root is null, that means we have reached the leaf node, and since it is a leaf node, we return 0 from here because it do not have any child. Otherwise, we recursively call the same function for the left subtree and for the right subtree, while we add 1 to the answers returned by the number of children in the left subtree and the number of children in the right subtree, plus 1, which accounts for the root node that we have here. So let's say we have root here, and then we have our left subtree. So for the root we have left subtree, and then we have our right subtree, and we call the count nodes function for the left subtree and for the right subtree. So let's say the number of nodes in the left subtree are x and the number of nodes in the right subtree are y, and the final answer for this entire tree would be x plus y plus 1, where 1 accounts for the root node itself, and that's what we are doing here. And this procedure will be recursively called for each node of the given tree. Fine. And in this way we'll be visiting all the nodes exactly once. Let's see time and space complexity for this particular implementation. We can see that we are visiting each node exactly once, and there are n nodes. Therefore, the time complexity is big O of n, while the space complexity is constant because I am not using any extra space to solve this problem. But stack space is indeed consumed, which would be big O of n, but the auxiliary space used is constant. So this was a depth first search approach, and it is one of the naive approaches to solve this problem, while the another approach to solve this problem is BFS or breadth first search approach, which is another graph traversal or tree traversal algorithm. Let's discuss that approach as well. So the BFS approach to solve this problem is also simple. So the prerequisite to understand this approach is the basic knowledge of BFS, how it works. Let's understand how BFS is used to count the number of nodes in the given binary tree. So this is our target binary tree. We take a queue and we push the root node inside the queue. So this is our visited array. So we know that in BFS we traverse the nodes level wise. So first we traverse the nodes in the very first level, then we traverse the nodes in the next level in this fashion. That means, so let's understand the BFS approach to solve this problem. So we know that in BFS we traverse the given nodes in a level wise fashion. That means we start from the root node and we push it into the queue. So this is our BFS queue, which will be used to store the nodes, and we mark the first node that is present at the very first level or the root node as visited. Then we pop the node from the given queue. So this is popped the queue, and we traverse the children of this node, that is exploring the next level of the given binary tree, and we check for all the unvisited children. So we see 2 is unvisited as well as 3 is unvisited. So we mark them as visited and push them into our queue. So 2 and 3 are marked visited and we push them into our queue. While we are performing BFS, we are keeping track of a count element which is initialized to 1 when we pushed the root node into the queue, and it is incremented whenever we push a new element into the queue. So since we pushed 2 and 3 into our queue, the count is incremented to 3. Then we pop the least recent element from the queue, that is 2, and we simply explore the children of this node 2 in the level wise fashion, that are 4 and 5. So we visit them, so we mark them as visited and we push them into the queue, while the count is incremented to 5. Now we pop the least recent element from the queue, that is 3, and we mark this 3 as visited. So we pop the least recent element from the queue, that is 3, and we explore the children of this node 3, that is node 6. We mark this node as visited while we push this node into our queue, and the count is incremented to 6. Then the remaining nodes are popped out one by one because all these nodes, that is 4, 5 and 6, do not have any children, and we end up with the empty queue. And there we quit our BFS, and the final answer will be 6. That means we have 6 nodes in the given binary tree, which is the answer, and we have visited all the nodes of the binary tree. So this is the BFS approach. Let's see the implementation for this approach. So this is the implementation. For this approach. The countouts function takes in the root of the given binary tree. This is the base condition where we are checking if the root is null. That means we have empty tree. In that case, the number of nodes will be 0. Then we declare a queue and initialize the queue with the root node and initialize answer with 0. Then we run our BFS and we run till the queue is not empty. We calculate the size of the queue and we iterate over all the elements of the queue, and for each element we simply push its left and right child if they are present into the queue, and for each node from the queue We are simply pushing its left and its right child into the queue while we pop the current element out of the queue. That means simply storing the children of a particular node, and we are incrementing the answer by 1. So since we are popping one node from the queue, the answer is incremented by 1. That means we are exploring that node. After we have exhausted the queue, the answer will store the number of nodes in the binary tree, and hence we return the answer right from here. Since we know that this is just a standard BFS search, for BFS the time complexity is big of, where n represents the number of nodes and e represents the number of edges, while the space complexity is also big of n plus e because of the queue and visited array that we use. While performing the BFS. Let's see the implementation of the BFS approach here. So this is our solution class, which has count nodes function, which takes in the root node and returns the number of nodes in the binary tree represented by this root, where this is the structure for the tree node. It has a value, that is the data, and a left and a right pointer, while this is a constructor used to initialize these variables. So first we'll handle the base case, that is the case of empty tree. If the root is null, we return 0. So in case of empty tree, the number of nodes in the tree are 0. Otherwise, we initialize a queue, and we initialize this queue with the root node. Then we use our while loop. While the queue is not empty, we calculate the size of this queue and we iterate over all the elements of the queue. So here we are checking if the current node that we are considering from the queue has a left child, then we push the left child into the queue. If it has a right child, then we push the right child into the queue, and we pop the current node from the queue, and the answer is incremented by 1 because one node has been visited. Finally, we return the answer from here, which stores the number of nodes in the given tree. Fine, so this is the implementation of the BFS approach for the given problem in C++ programming language. Let's see the implementation in other languages. So I have attached the codes in the description below, so make sure to check it out. And that's all for this video. If you like the video, then do like it and make sure to subscribe to my YouTube channel and give your feedback in the comments below. I will see you in the next video. Till then, take care. Bye bye.